Welcome to the 8th video lecture on Module 3 of Basic Electrical. In this, we will be seeing the generation of three-phase AC voltages and the need for three-phase AC supply. First of all, let's see the need for three-phase AC supply. So, consider a single phase AC voltage. So in this we can see that the voltage is varying. It slowly increases, reaches the maximum value, then decreases, then at a particular instant it is 0, then again increases in the opposite direction, reaches the maximum value, then again it will reduces to 0. So here we can see that at certain instance the voltage is becoming 0. And the power generated in a single phase AC circuit at these 0 crossings will also be 0. So a non-uniform power is generated in the case of a single phase supply. Also, the power generated in a single phase system is less, and this is not enough to drive industrial loads which require higher power. So due to these drawbacks, we are going for polyphase systems, that is more than one phase. The commonly used polyphase system is the three-phase system. Next, we can see the generation of a three-phase AC supply. So, first of all, what is a phase? A phase can mean a coil, a branch, or a circuit. So, three-phase means that we need 3 sets of coil. So, for generating a three-phase voltage, 3 identical coils are placed at 120 degree from each other and rotated in a uniform magnetic field. So why the spacing between these coils is 120 degree? Because total we are having a 360 degree. So 3 coils means 360 by 3. So in total we need 120 degrees. So in order to generate a three-phase supply, we will be placing 3 sets of coils 120 degree apart. And these coils are rotated in the anti-clockwise direction. Okay. So first of all, consider the first set of coil, that is your R coil, or which is denoted here in the figure as red in color. So when we know that when one set of coil is rotated in a uniform magnetic field, we will be getting a single phase voltage. So the voltage generated in the across the coil R, that can be denoted as VR is equal to Vm sin omega t. Okay. And the waveform that can be drawn as shown in the figure. Now we can see that the Y-phase coil is kept 120 degree away from R-phase coil. So the voltage generated in the Y-phase coil will be 120 degree lagging from the voltage generated in the R-phase coil, that is Vy is equal to Vm sin omega t minus 120 degree. So voltage in the Y phase can be drawn 120 degree shifted from the R phase. So just like this. Then tracing towards the back, we can draw like this. So this is the voltage generated in the Y phase. Now regarding the B phase. So B phase is kept 120 degree away from Y phase, or in total the voltage generated in the B phase, that can be written as VB is equal to Vm sin omega t minus 240, or in another words we can write VB is equal to Vm sin omega t plus 120 degree. That is the B phase that will be starting 120 degree delayed from the Y phase, that is somewhere here. So voltage in the B phase can be drawn like this. Then tracing towards the back, this will be the voltage. So this is your 3-phase AC supply. So here we can see that at any instant of time, the total voltage in a 3-phase system, that will be the vector sum of the voltage in all the 3 phases. Okay. Also we can see that at any phase, any instant, if you are taking any instant, the voltage in any of the phases is having a peak value. So a uniform voltage is generated. So if we are taking this instant, we can see that even though the B phase voltage is 0, the R phase and Y phase is having some voltage. So there is no zero crossing point in the case of a 3-phase system. And also since the total voltage is the vector sum of all the 3 voltages, the net voltage is higher than that of the single phase system, and hence the power generated is also high. Next we can see the phasor diagram of a 3-phase system. So 3-phase voltages, they are denoted as VR is equal to Vm sin omega t, VB is equal to Vm sin omega t plus 120, and Vy is equal to Vm sin omega t minus 120. So VR is taken as the reference phasor here. Then VB phasor, that is delayed from the R phasor by 120 degree. So it is drawn downwards. Gap is 120 degree. Then VB phasor, that is delayed from Y phasor, or it's lagging the Y phasor by 120 degree, or in another words we can say that it is leading the R phasor by 120 degrees. So it is drawn upward. So this is the phasor diagram of the 3-phase AC system. Now the commonly used term in this 3-phase AC system, that is known as the phase sequence. So phase sequence is actually the order in which the voltage in each phase will reach their maximum value. So if you are looking at the above phasor diagram, we can see that these phases are rotating in the anti-clockwise direction. So the phasor will be having its maximum value when it is vertically upwards. So when these phasors are rotated in the anti-clockwise direction, we can see that first R phasor will reach the maximum value, then Y phasor will be reaching the maximum value, then after that B phasor will be reaching the maximum value. Hence, the phase sequence in the above mentioned case is RYB. That is the order in which the voltage in each phase is reaching their maximum value. Now let's see the advantages of a three-phase system. So first advantage is that for a given frame size, the three-phase system has a greater output than a single-phase system. Why? Because with the addition of just 2 coils, we can see that the output voltage generated is higher than that of a single phase. So since output voltage is high, the power generated will also be high. Now the second advantage is that the three-phase system requires lesser amount of conductor material. Okay, so let's see. Assume that I am having a single phase supply, this phase, then neutral. Okay, then I am having 3 loads. This is my load 1, this is my load 2, and this is my load 3. Okay, so for connecting these loads to the supply, let's check the number of conductors required. So this is first conductor, second conductor, third, fourth, fifth, and sixth. So a total of 6 conductors are required. Then what about a three-phase system? What if the connection is three-phase? So first of all, we can draw a three-phase having R phase, Y phase, B phase, and neutral line will also be there. So in the case of three-phase, what we'll be doing is that these loads that can be connected like this. Okay, and one end will be connected to R phase, the second end Y phase. Here this will be connected to B phase, and common point to the neutral. So here we can see that only 4 conductors are used, and all the conductors, all the loads are connected between a phase and a neutral. So if we are checking over here, the first load that is connected between R phase and neutral, the second load that is connected between Y phase and neutral, the third load is connected between B phase and neutral. So by using 4 conductors, we can connect 3 loads. So lesser number of conductors are required in the case of a three-phase system when compared with the single-phase system. So that is the second advantage of three-phase supply. Then third advantage, that is regarding the three-phase motors. So in the case of three-phase motor, they are having a uniform torque. Why? Because the voltage is uniform. Because if you are checking the three-phase supply voltage, we can see that at any instant of time, the voltage in any of the phases will be having a peak value. So there is a uniform torque in the case of a three-phase motors. But in the case of a single-phase motor, the torque developed will be pulsating. Why? Because the voltage itself is a pulsating voltage. Single-phase voltage is like this, right? So during the positive half cycle, what happened is that if this is your motor, it will be rotating in the clockwise direction during the positive half cycle. And during the negative half cycle, the torque developed will be in anti-clockwise direction. So the torque developed itself is a pulsating torque. Then This have one more disadvantage, that is the motor, the single phase induction motors. These motors are not self-starting due to this pulsating torque, because the motors will only be oscillating. During positive half cycle it will be rotating in clockwise, and during the negative half cycle it will be rotating in anti-clockwise. So that is the fourth advantage when we compare with the three-phase system. That is, in the case of a three-phase induction motors, they are self-starting because the torque generated is rotating, but in the single phase motors they are not self-starting. Then the fifth advantage is that the three-phase motors are cheaper and efficient when compared with the single phase motors. So these are the advantages of a three-phase system when compared with the single phase system. So that's the end of this video lecture. Thank you.